So today we're going to wrap up everything series, and we're going to look at the last application, which is actually, oh, I don't know if I should use the word fun, but it's kind of fun compared to everything else, because we've looked at a few different types of series, and we've been concentrating on the tweakages. Get rid of that thumbnail there. Oop, hold on a second. There we go. We've been working on the tweakages, and I'm going to point out the three particular ones that we use the most. I'll write it in this form to simply. Does anybody know what these are? These are the three that are by far the most used. I'm just curious if you recognize. Like, what's the first one, for example?
E to the
Just
X.
e to the x.
E to the X. And the second one?
Cosine?
Cosine.
No, it's yeah.
Yeah.
Cool.
And the third one, this is the geometric. These are the three most common ones. And the fact that you guys actually recognize a couple of them right off the bat is really good. Not critical, but good. Because when you're sitting in my Math 255 class and these come up, the ability to recognize this is really, really helpful. So what we worked on last week was what I called the tweakages. So if I asked you to do, what is x squared times e to the 3x, then you could tell me it's x squared times n equals 0 to infinity, 1 over n factorial, 3x to the nth power. And so now when I simplify it, I would have a 3 to the n over n factorial, x to the n, x squared. And that's awesome. Now, by the way, just so you know, you don't put the x in the quotient. There's a really simple reason. Power series, x to a power, has to stay completely separate from the coefficient, because that's an, that's my x to a power. You always keep them separate. Now, there was nothing about that I think any of us find taxing. So my question is, what if I gave you that and I asked you where it came from? Now, that might be a little bit of work. So that's what we're going to do. We're going to look at some very kind of standard forms of things we see. Now, I mentioned before, if I just randomly made up a power series, just made something up, it didn't come from a particular.
I have a quick question about what you just raised. You said the sum of n to infinity of x to the n equals 1 over 1 minus x. Is it supposed to be plus x?
Series. That's the geometric series.
All right, so it's supposed to be minus x, not plus x, because then I have it wrong in my notes in a lot of places.
But think geometric series. What's the 1 over 1 minus r?
Yeah.
Do it longer than any of them. Yeah. Not 1 plus r, 1 minus r. Yeah. Now the binomial expansion has a plus. That might be what you're confusing with. Okay.
That is what I'm confusing it with.
And they do look enough alike that you gotta, that's the tricky part, keeping them separate, of course. So what if I just made up, I'm gonna make up one. Okay, just gonna make something up off the top of my head. I've got -1 to the n over n squared plus 2x minus 3 to the n, and n's going from 0 to infinity. Okay, this is a power series. You can evaluate this. It's centered about 3. But I can't tell you a function that it came from. I can't tell you a function that I took derivatives of and created a Taylor series for. Why? Because there's an infinite number of variations of this type of question, and most of them don't come from somewhere. I'm just making this up. But if I have something that came from an e to the x or cos x or a sin x or a log x or an inverse tan x, there's not that many that we would actually use. The form is what you would recognize. Okay, there's nothing about this that's special, and there's nothing about the form that's special. So what if I started with something, and I'll go through each of these so that hopefully they're somewhat recognizable. I have something of the following form. N equals 0 to infinity, -4 to the n over 2n factorial x to the 4n plus 3. And I'm telling you this comes from a function. And I would like to work backwards and figure out what the function is. Now, knowing that the three forms we're most likely to see are the e, the cosine, and the geometric. It could be something else, but these are the ones we see the most often. Which of the three does this most resemble to you, and why? Anybody?
Cosine.
Sine.
Why the cosine?
Or cosine, yeah.
Giveaway.
Because you have 2n factorial in the denominator.
That's really the biggest, but what else do you have?
Alternating.
You have an alternating series with the 2n factorial in the denominator. You're going, that smells like a cosine. Now it doesn't, it's obviously not cosine x, just straightforward. It's been tweaked. So what I want to do is manipulate the terms. For example, -4 to the nth. Can I write that as -1 to the nth times 4 to the n? Can I do that? Is that legal?
Yep.
Everybody okay with that? I can do that. Okay, so I want to do that because I want it to have that form, like you just said, that it looks like a cosine. So now it's -1 to the n over 2n factorial. And now I have a 4 to the n x to the 4n plus 3. That plus 3. Do you like that one? I don't like the plus 3 at all. Can I do anything about the plus 3 part?
Can't you pull it out and have it as x cubed?
Can I think of this? This is what I think. This is what you're saying, Tom.
Yep.
Yep.
So can I then put the x cubed completely in front? Now I have 4 to the n x to the 4n. Ooh, this is getting better. Okay, so far so good. I mean, we can say absolutely we're certain these are equal. Not quite yet. I need something. What needs to be sitting here? I need something raised to what power exactly?
2n.
I need something raised to the 2n power. How am I going to do that?
Well, it's just x squared raised to the 2n power, right?
Okay, the x, you're absolutely right. The x is not so bad.
It's just the 4 to the 2n. Sorry, 2 to the 4.
Yeah. 2 to the 2n.
Can I think of this as being 2 squared to the n? Is that legal? Is 4 to the n the same as 2 squared to the n? Yes, no, maybe.
Yep.
Yes, yes.
100%.
And can I think of this one as x squared to the 2n? I think that's what you guys said. Can I think of it that way?
Yep.
So now what do I got? I have 2x squared. Let's check it out. Remember, a product to a power, just to remind us in general, if I had a, b to the nth power, that's a to the n, b to the n. That's just a basic exponent rule. So this would be 2 to the 2n, which, okay, that's 4n. X squared to the 2n, okay. So I know that's okay. So the last tweakage. Okay, is what? What did we just say? 2x squared to the 2n. That's my thing. That's my argument. So can you tell me what this is?
Cosine 2x squared.
Crowd goes wild, confetti everywhere. It's like a game of Clue, right? Mr. Green in the parlor with the hacksaw. I don't know if that's actually possibilities, but might as well be, right? That's it. And I can always work backwards. So this power series came from this, but we worked backwards. Now working backwards obviously is trickier because we are starting with the assumption that this actually exists. It wouldn't require a whole lot of tweakage before we run into dead ends. So we're not going to look at problems that are dead ends. So it's kind of cool. And really the key was you recognizing right off the bat what was the most likely scenario. Now let's do another one. Okay, let's try. This might be a little bit easier. Okay, now I've got that. does this look most like? Well, what is it missing? If you could say it's missing something, what's it missing?
N factorial.
It's missing factorials. And we know exponentials and sines and cosines all have factorials. This is missing a factorial, which really only leaves one. What would that be?
Binomial.
Geometric.
Geometric. Yeah. Well, binomial we can write in this form, but the thing is even in the binomial, we usually see some pattern of factorials. They may cancel on us, but I don't see a factorial. So what I'm going to look for is I need it to look like this. This is what I need. If I can make it look like this, then I can answer the question. Do you think this is going to be really hard to do?
No.
Not really, but it's that kind of stuff. Do you agree that it's that kind of stuff that kind of gets in the way? So can I work with that first of all?
Just split them up. So you could say
Split them up.
like 1 over 2 to the n times 2 to the 2 squared.
Okay. Perfect. And how about the next one?
You could just pull the x squared out like we did last.
Now, I can't mess with these guys in terms of moving them around. They got to stay inside, but these guys I could pull out, couldn't I? In other words, n is the index, so n's got to stay there. Think of like n's the variable, really. So I've got an x squared and I've got a 2 squared. Can I write it like this? Is that legal? These guys.
Yeah.
Now what am I left with? 1 over 2 to the n, x to the 2n. I think I'm almost there. I need to write this, how? As something,
X divided by 2 to the n.
Careful.
X squared over
Yes.
2 to the n.
Yeah, so how if I do this? Is that legal?
Yes.
Yep.
No,
Can we
you have
go?
a 2 there, not an n.
Oh, thank
Yeah.
you.
exponent.
2n.
Thank you. And then, can I go directly now to the form of the geometric? In other words, can I go to my quotient? Well, what's the form? If it's r to the n, we just said it's 1 over what?
1 minus
1 minus.
the r part, which is minus 1/2 x squared.
What's left to do? I guess just if I multiply, I'm gonna have an x squared on top. 4 minus 2x squared. Is there anything else I can do algebraically, or is that probably as good as it's gonna get?
I think this is it.
That's probably as good as it's gonna get. Now, is this always true? Is there a restriction? Yeah, remember the old absolute value? of
For,
R?
Absolute value of r less than
Yep.
1.
So that means 1/2 x squared, which is already positive, by the way. It's got to be smaller than 1. So x squared has got to be smaller than 2. So x is in absolute value has got to be smaller than √2. There's my restriction. Okay, this is important because remember, these are only true. The r to the n, 1 over 1 minus r is only true when this is true. So I really do have to throw that in. But this is equal to this, okay, as long as that's true. Pretty good. All the forms, the geometric is usually the least amount of work, and partly because there's no factorials.
Professor-
Try one more of these bad boys. Question?
Well, could we have a problem where the factorial was factored out at some point?
Well, the problem is the factorial is always going to involve an n. So anything with an n can't be pulled out of the summation because the index is n. In other words, that's the only thing that's untouchable. That's why x's to x squareds and 2 squares, those can be pulled in and out because they're literally constants. In terms of a summation, they're treated just like constants. All right, let's do one more of these. Let's do the sum of 1, 3, that's it. Sorry. So when I'm looking at this, again, I got to categorize it. It's not a cosine. How do you know it's not a cosine? Or a sine?
There's no,
the n factorial.
It's n factorial instead of a 2n. It's not geometric because there is a factorial.
It's not alternating.
Well, alternating, we can always manipulate and change the alternating part. That's actually not that hard. Believe it or not, changing the alternating is not that hard. You just make it so it's negative x raised to a power, and then
Is
but-
that the e to the x?
it's going to be e because it's just an n factorial. So it looks most like e. So with e, remember e, I'm going to have 1 over n factorial x to the n. Okay. I got 3. But e is really, remember, that's the form of e. 1 over n factorial thing to the n. So can I make this thing to the n? I might, except again, I got this dangling. What do I do with that guy?
Pull them out.
So how would that look?
1 over x to the 4th.
Oh, okay. And this guy, that can come completely in front. There's no n. So this guy absolutely can come in front. So you guys are on right now. You are, as we say, you're like butter. You're on a roll. Okay. I've got 1 over n factorial. Now what's left? I've got a 3 to the n and an x to the 4n. Do we agree? So far, so good? Let's stare at that for a
And then we
moment.
can-
Sure we haven't changed anything. Okay, I need now to make this guy something to the nth power. What would that be, do you think?
just be 3x to the 4.
So it looks like 3x to the 4th to the, so 3 to the 4th, boom. I think we're good. So we can now say 1 over n factorial, 3x to the 4th raised to the nth power. There's my thing to the n. Can we now write the function?
E to
1 over
the
x 4th, e
3x
to the
fourth.
3x to the 4th.
You did the 3x to the 4th. You could say 1 over or,
over
Just do
x
that.
squared.
yeah, we did it. So once again, all right.
Those are easy.
Yeah, easy is relative. I think they're actually kind of fun though. I think you'll like these because you're told there is something at the other end. Problem is, if I said, is it possible there's something and maybe there's not something, and now I'm beating my head against the wall trying to figure out something that might not have an answer. No, there is something at the other end. I'm already told that. I'm just figuring it out. So this is really a case of reverse engineering.
Yeah,
Meaning
this
I
is
didn't-
honestly, this is sticking a lot better than the other lecture we did about it.
Well, if I start with this, every one of you could get to here. This is much easier to go this way because it's called the tweakage. If I start here, it's actually more difficult than here, but you have some background at this point.
Also true.
You said, I know this looks like this, and that's kind of the key. I'm making them look together. So this now is the end of everything series. Now we're going to move on. And so when we use terms like conic sections, that term sometimes doesn't even ring something. Where does that term come from? Does anybody know when we say conic sections? Because this is considered really important. Of all the geometry you've ever learned, this is the stuff you're actually going to use the most, believe it or not.
It's just taking a slice out of a cone.
Yeah. So picture the following. I'm going to go back to, low level. Okay. Now, technically, think of this as being infinite. Think of this as a circular cone. That just means the cross sections are circular. The word cone doesn't mean it's necessarily circular, but that's what we're going to use. Now, if I slice this thing, this is supposed to be three-dimensional. If you're fortunate, maybe in junior high or high school, you had a physical model, whether it be made of plastic or it was made of wood that you could slice and take apart. And I think it's just a great visual to understand. So if I did a slice that was horizontal, then what is my cross section looking like? Anybody? A perfectly horizontal cross slice what would that cross section look like?
A circle.
That would be a circle. So a circle is a conic section. A circle is the only conic section we're not going to bother with right now. We look at those later on. A circle is not special or specific enough. So I want to do the same thing, But instead of doing a horizontal slice, I want to tilt my slice. Oh, okay. So if I tilt my slice, now what does my cross section look like?
An oval.
That oval, there's a name for that. What's that called?
An
It's
ellipse.
almost like when
No.
An
the moon
ellipse.
goes in front of the sun. It's a similar sounding word.
Ellipse.
Ellipse.
I like how we're all so confident about that.
And so a circle, just so you know, I mean, absolutely mathematically, geometrically, in every conceivable way, a circle is a special case of an ellipse. A circle is an ellipse, but it's an ellipse with certain restrictions. And so it's sort of like if I'm talking about rectangles in general, a square is a rectangle, but it's very special. So when we're talking about rectangles, we're usually not thinking of squares particularly. When we're talking about ellipses, we're usually not thinking about circles because I would need more information, more specifics. So think ellipse. All right, now if I take this same thing, remember this shape is infinite, but I slice it in such a way that I go through the open section here. Now
Well,
that's
it's
a little bit
infinite.
trickier. That is the parabola. That might not seem obvious, but we'll do things because again, you're looking at my two-dimensional drawing. And the last one, if I slice, people say, why do you always make two when you're talking conic sections? It's for the third one. What if I slice this thing perfectly vertically? Now I have two pieces, one going in each direction. And they're not parabolic at all. They're not even like parabolas. They're actually much closer to triangles, in fact. What is that one called when I slice both pieces? Anybody remember? I'll give you a hint. It starts with an H.
Hyperbola is.
Close.
Hyperbola.
Hyperbolas.
Hyperbola. Yeah.
I think the hyperbole is something in English, right?
I don't know.
It's an English term. I don't know what those are exactly, but this is a hyperbola. So ellipses, parabolas, hyperbolas are the three guys we're going to study over the next couple of days. And I said, why? We did these in elementary school. We did this in junior high. We did this in high school. Yeah, we learned what the shapes look like. We learned a little bit about the geometry and the algebra, and that's fine. The reason we're studying these now is because next semester in Calc 3, when we get to the three-dimensional stuff, these are going to be the most common things we work with. Three-dimensional versions of these. Oh, and when I'm looking at an equation, I have to know what the equation looks like. Kind of like right now in Calc 1, when you were finding areas and you were rotating things to find volumes, you needed to know what the region looked like or you couldn't set up your boundaries. Well, if I'm doing something in 3 dimensions and I'm trying to find volume or surface area or different things like that, I need to know what it looks like in order, again, to set up my boundaries and to work things out. And the most common shapes we work with are conics because the algebra is very friendly and because they actually do show up a lot in reality. Okay, and so we're going to review these. So today we're going to review the parabola, but we're going to do it from a strictly geometric point of view. Everybody's done parabolas at different points in their lives, and they've done it from different applications. So I'm going to give you, first of all, the basic algebra application. This is not the one we're going to do. This is the same one you do in a Calc 1 class. In reality, if you've ever taken a business class, okay, the most common, the only shape you even do are lines and parabolas, and there's a reason for that. So let's suppose this is, this is money, this is production typically. Instead of time, it would be production. So numbers of things produced. In a typical business model, in a typical classroom, you overly simplify things. I don't want to say you dumb it down. You just use really basic ideas. You use things like the supply of the law of supply and demand is linear, which it isn't. So as things increase and other things decrease, it always stays linear. So the more I produce, the cheaper there will be. But from a linear standpoint, that's really not reality. But we do that because algebraically, it makes it so much easier. So revenue is always the same thing. Revenue is how many you sell multiplied by what price you got for them. That's what revenue is. Cost is how much it costs to produce things. So in the overly simplified examples that we do in algebra and basically business calculus, you always operate kind of the same idea that cost is going to be linear, which it isn't. It always costs the same amount to produce items, even if I produce a few, if I produce a lot. We know that's not true. We know as production increases, costs tend to go down per item. But if we pretend that cost is just a constant multiple of how many I produce, and revenue is simply how many I produce multiplied by how much they sold for, then profit, which is the difference of revenue and cost, profit always looks exactly the same. And this is why they do the overly simplified case in the other classes, is so that you have a starting point. So the typical model looks like this. This is the typical universal model you're taught in algebra, calc 1, business calculus, a downwards opening parabola. Why? Because if I say everything's linear, then revenue is going to be a quadratic, profit's a quadratic because it's a revenue minus linear. Again, overly simplified. But there's really important things. For example, that amount right there, this is negative. This is money. This is called your overhead, your fixed cost. Before I produce a single item, I still got to pay rent. I got to pay the utilities. I got to pay bills. Does anybody know what we call that?
Will you break even?
Yeah, there's a name for that. You've all heard it. You may not think about it. It's called equilibrium.
Yes.
Okay, that's, when you think about it, if my equilibrium's off, what aspect of my life is affected? My
Balance.
My balance. That's what equilibrium means, balance. I'm balanced. I'm not making money. I'm not losing money. That's called equilibrium. And I need to know where that is. This is the other equilibrium. This means I have too many on the market and now the price is going down. That's bad. This means really bad. And what is this?
Max profit.
That's the maximum profit. That's what I'm striving for. How much do I charge? That's what you do in a basic business model. And this is what they study in business calculus. A downwards opening parabola is always the model. It cannot be an upwards opening parabola. There's no scenario where the more I produce, the more I can sell it for. So if I have infinite production, I can sell for infinite money and make infinite. No, it doesn't work that way. The law of supply and demand says if you have a shortage, you make more money per item, but you don't make a lot of money overall because you're not selling that many. If you have a glut, you charge a lot less per item, so you're not making a lot of money because you're not charging anything. There's a happy place right up there. Now, that's the algebra of parabolas. And that's really easy to work with because I can find the that guy right there is called the vertex. I can find it using baby algebra, using calculus, derivatives. All of that stuff is correct, but that's not what we're interested in. We're interested in the geometry, which is not even similar in any conceivable way. So now we're going to define what a parabola is. Okay. Parabola. The set of points on a plane. By the way, I actually have to put the on a plane part. If I say the set of points and I give you some conditions, the default, believe it or not, is actually three-dimensional, not two-dimensional. A simple example, the definition of a circle is the set of points on a plane that are equidistant from a given point. The definition of a sphere is the set of points that are equidistant from a given point. Wait a minute, that's the same definition. Not exactly. The definition of a sphere is the set of points equidistant from a given point. Circles the set of points on a plane. Oh, so if I don't say on a plane, then it's automatically three-dimensional, and that's why it's a sphere. That's what we always actually have to say on a plane if I'm talking two dimensions, because the automatic default would be three-dimensional, and we're not doing three-dimensional conics today. That's next semester. The set of points on a plane, equidistant.
Well, you said next semester or next class?
Calc 3.
Oh shit, yeah, okay.
We study these in terms of their three-dimensional ramifications, but you'll already know what you're doing, so it's not like you have to learn something new. Equidistant from a line, which I'm going to define, and a fixed point. The line is called the directrix. The fixed point is called the focus. So the definition of a parabola is the set of points on a plane equidistant from a line and a fixed point. So I start the parabola with a line and a fixed point. So here's my directrix, and let's say that's my fixed point. Okay. Where's my parabola? Now I got to find all of the points on the plane that are equidistant from the two of them. Now, just so we remember, sometimes it's not always obvious, some of the geometric facts that we use. Okay, if I'm holding a point between my fingers right now, it's really small. If I drew line segments from that point to my floor, how many line segments could I draw from this point to my floor?
Infinite.
Infinite.
Infinitely many. Only one of them represents the distance, though. How do I know which one's the distance?
The shortest.
Shortest one.
And which one will that be? If I hold this,
Vertical one.
everyone does this and I drop it,
Radius,
the perpendicular is always the
the
shortest.
perpendicular.
And now we know that, but we may not remember that. That's a very basic postulate from geometry, but the closest distance is the perpendicular. Okay, so if I drew an infinite number of line segments from this point to the line, the closest one, do you all agree would be that one? It's actually a simple geometric proof because every other one would represent the hypotenuse of a right triangle, and the hypotenuse is longer than the legs. But okay, that means that the point that's equidistant between the point and the line, there's a point halfway between them. Does everyone agree?
That's the
Halfway
focus.
between this, there's a point. That's the most important point on the parabola. It is? Yeah, that's invisible. That's invisible. I don't see the line. I don't see the focus, but I see this point. What's that point called? Anybody know? I've used the term already. Starts with a V.
Vertex.
With an vertex, good. That's called the vertex. That's the point that's the closest to both the focus and the directrix. Now, as I'm moving, I'm just sort of going to visualize maybe about there. All right, let me go on a little further, maybe about there, right? If I keep drawing line segments, maybe about there and maybe about, I don't know, there and so on. What's going to happen is I'm going to use this curve because every point on my curve, these two distances have to be the same. That's what it means to be equidistant. Question?
I was gonna say, how are you figuring out those other points? But you
Well,
just
I'm
said
right now just kind of visually the set of points where if I actually measured, take every point on this curve, if I measured the distance from here to here and the distance from here vertically perpendicular to here would be equal. It's going to form this curve, and that curve is called the parabola. I don't see the directrix and the focus, but they are definitely there. Think of them as guides to get there.
do all parabolas have the same like rules? Do all of them have the equal distance?
Also, and which one is the focus again?
The focus is the fixed point, the directrix is the fixed line, and now I'm figuring out. So what happens if I move the focus closer to the line or I move the focus further away from the line? Well, it'll change the shape of the parabola. I can make the parabola skinnier, or I can make the parabola flatter by moving the focus. In fact, leave the line alone and just move the focus up and down. Does that make sense? Oh, so if I move the focus, that means it's probably way flatter. If I move the focus really close, it's going to be way skinnier. We're going to show that in a moment. So what we'd like to do is use that information to figure out how to come up with the equation of the parabola. Okay. Now, let me go back to baby algebra again for a moment. When we did parabolas, and by the way, we're only going to concern ourselves with vertically opening because we want them to be functions for now. Yes, parabolas can be horizontal. I'm not worried about those because that just is one more set of rules that's confusing. So right now, we're only going to worry about vertically opening parabolas. So from baby algebra, we know the form of any parabola, any quadratic function. We remember this. Okay, the A was important. If A was positive, it opened up. If A was negative, it opened down. If A was large, it was skinny. If A was small, it was flatter. And from there, we could figure out the vertex. Remember, we did stuff like that. You completed the square, you found the axis of symmetry. There was all sorts of stuff you did in algebra to figure it out. But that was the sort of the generic form of the parabola. And that lead coefficient told me a lot about the parabola because it told me everything about its shape. Okay, so I'd like to know, will that show up in what we're doing? Yeah, actually it will. So let's consider, let me start with a simple case. Let's consider a parabola where the vertex is actually at the origin. This will make life easier. Okay, let's just consider, I have a parabola and the vertex is at the origin. We can move it around all you want. Okay, now I will give you examples of that in a moment. In fact, I'm gonna make it really easy. This is something you already know from baby algebra. Okay. if I have a circle and my circle is centered at the origin and my circle is of radius r, we know the equation of this circle is this. Everybody agree with that? Everybody knows it, right? Circle of radius r centered at the origin looks like that. But the question is, what if my circle is not centered at the origin? What if it's centered somewhere else? Oh, same circle, same radius. But what if my circle is centered, I don't know, at h comma k?
X
Oh.
minus h, y minus k.
Beautiful. And because you know where that comes from? That comes simply from the distance formula.
Yep.
Oh, so if I move my center, and the reason is, if this point right here is x comma y, then x minus h quantity squared plus y minus k quantity squared equals r squared. That's just Pythagorean theorem. Oh, so the circle, when I move it to hk, the h and the k show up. So we're familiar, this is a pre-calculus notion, right? When I move a shape up or down or sideways, we know how it's changed. When I move it sideways, I do that. When I move it vertically, I do that. When we figure this out, then we'll move the axes, we'll move the shape. That's the easiest part of the problem. It's figuring out the relationship between the vertex and the focus and the directrix. So in my picture, there is most definitely a focus. There is most definitely a directrix. So let's say the directrix is about here. And let's say the focus is about here. Okay. Now, because we know that the vertex is equidistant from the two, we usually use the value p. I wasn't there when they decided, why p and not, f for focus or something. So that point will be at 0 comma p. P is usually referred to as the focal length. So if that's 0, 0, and that's 0 p, then what would the equation of this line be? It would be y equals what?
Negative p.
Perfect, because we just said they're equidistant. Okay, so I'm giving you the setup. Don't worry about the perfection of my drawing. If I have this drawing and that's the focus and that's the directrix, then here's what I can say with certainty. Let's take any point on the parabola, call it x comma y. Again, don't go by the accuracy of my drawing. If this is a point on the parabola, then this distance and this distance must be equal. Okay, so for lack of a better name, let's call this distance, how about d1, and let's call this distance d2. All right, and they absolutely must be the same. Well, according to the distance formula, isn't d1, remember how the distance formula works? Change of x squared plus change of y squared. So I'd say x minus 0 squared plus y minus p squared. Okay, what's d2? Well, that's easier because this is vertical. I'm going from x comma y to this line. It's only the y distance. Well, if that much is y, then how much is that?
Y plus p.
Y plus p. Beautiful. So therefore, d1 has to equal d2. Okay. Well, I got that square root on the top is going to make this kind of tricky unless I do what? Algebra. What can I do?
On both sides.
Yeah, square both sides. Ah, okay. So if I square the left side, I'm going to have x squared plus y minus p squared. If I square the right side, I'm going to have y plus p squared. Oh, okay. Now, since this is a function, I would really like to write it as y equals. Before we said f of x. It doesn't matter if you said y or f of x, but I'd really like to isolate the y. I got y squareds though. Is that going to be a problem? Well, I got one on each side. So what's probably going to happen?
Cancel out.
Probably going to cancel. So let's go ahead and expand both of these. So on the left side, I have x squared plus y squared minus 2py. P is a constant plus p squared. On the right side, I've got y squared plus 2py plus p squared. Does anything cancel? Oh, yes. Boom. Boom. Wow, what does that leave? That only leaves that, than that. So why don't we send that guy packing? So right now, the left side is x squared. What's the right side? If I throw that on the other side, remember there's an equals here.
4py.
4py, and we said we'd like to write y equals. So wouldn't that be y equals 1 over 4p times x squared? Does this look like the classic y equal x squared shape, basically, because I put the vertex at the origin? Is that what you're seeing there, hopefully? Yeah. Well, it turns out the coefficient in front of the x squared tells me a lot of information. It tells me exactly what the focal length is going to be, because whatever's the coefficient in front of the x squared is 1 over 4p. So I can always figure out what p is. Cool. Now, let's tweak this one more time. That was the parabola whose vertex was at the origin. Let's do the exact same parabola. This is the exact same parabola, folks, except now I'm going to put the vertex at h comma k. Same parabola I just had. Nothing's different. You know, focus, directrix. What's the equation of this parabola based on what we did earlier? Shouldn't it be y minus k equals 1 over 4p times what?
X minus h squared.
Oh, well, how about if I rewrite it like this? Y equals 1 over 4p x minus h quantity squared plus k. Now I'm gonna take you back a little bit again. In baby algebra, this is what you did. You did this. When you had f of x equals ax squared plus bx plus c, you either completed the square or you used the axis of symmetry to figure out where the vertex was. Unless you forget, you always then wrote your answer in this form. Does that ring a bell? This is what you do in every algebra pre-calculus problem. You did whatever factorization was necessary to get it to look like this form. Isn't this exactly the same form verbatim? I'm even using the same HK. Yeah. Remember I said the coefficient in front of the x squared tells you everything you need to know? If that's positive, it opens upwards. If that's large, it's skinny. If it's small, it's flatter. That coefficient turns out to be exactly 1 over 4p. So what we already knew from baby algebra, we didn't know what the relevance of A was. Now we know exactly where A comes from. Whoa. So here's how it's going to work. If I give you the equation, you can tell me everything about it. You can tell me the focus, the vertex, the directrix, the axis, all these things. If I give you any of those things, you can tell me the equation. So we're going to look at it from both points of view. Okay.
Wait, so the focus is P, right?
The focus is a point. The distance from the focus to the vertex is P.
Okay, how do you figure out the directrix then?
Well, because it's continued P in the other direction.
Oh, okay. Are we
Remember,
going
it's a line. So in this problem right here, let's do this. In this problem right here, my vertex is the point h comma k. My focus is what? Well, let's see. Am I moving vertically? Am I moving vertically or horizontally to get to my focus?
Vertically.
I'm moving vertically, so I'm going to add to the y coordinate, not to the x. So it'd be h comma what?
K plus p.
K plus p. Perfect. Now the directrix, that's a line. That's the line y equals whatever way you went to get to the focus, go the other way to get to the directrix. But that's not a point, that's the line. Ah, well, that wasn't very complicated. So let's throw in some actual values so we can see where the calculation comes from. All right, so let's suppose, oh, by the way, in all of this, where is the axis of symmetry? Because it turns out in a parabola, absolutely the first thing you can always find is the axis of symmetry. So again, lest we forget, regardless of what, maybe it opens this way, it doesn't really matter. If this is the point h comma k, the axis of symmetry is the vertical line that passes through the vertex that acts like a mirror. This looks exactly the same on one side as it does the other. So if my vertex is at h comma k, what's
x equals what? X equals H.
Exactly. That's why I said usually the axis of symmetry is the first thing you can find in a parabola. And if you don't remember, the axis of symmetry is the line x equals in the ax squared plus bx plus c form, is the line equals negative b over 2a. And if you forget, you can always take a derivative. You get the same thing. Axis is the fastest way. So let's consider, my pens are dying on me. Hold on. I need a blue pen with more juice. What happens? There we go. Pandemic pens. I have lots of black ink refills. I'm out of orange and I'm out of blue. Apparently I use way too much of each. All right, let's consider y equals, now I don't care if you say y equals or f of x equals, it's the same thing. Negative a fourth x squared minus 2x minus 2. Okay, now tell me a little bit about this parabola. What absolutely do you know about this parabola?
It
It
opens
equals
down.
-2.
It's
Downwards.
yeah.
Is it going to be really fast and skinny, or is it going to be kind of slower moving?
Slow.
Slower moving because it's 1/4 as opposed to a large coefficient. So I know it's going to open downwards, kind of slow moving. What I don't know is where on the XY plane it is. So I need the vertex axis of symmetry. I need all that stuff. Well, how do I find that stuff? Well, like I said a moment ago, finding the vertex is usually the easiest. Okay. I'm sorry, that not the vertex, sorry, the axis of symmetry. So lest we forget, again, in the form, in this form, remember the axis is always the line x equals negative b over 2a. And by the way, that also comes directly from the quadratic formula, in case you forgot. Oh yeah, that's the first part of the quadratic formula, right? So in this case here, my axis would be x equals what? It'd be
2
negative,
divided by 1/4.
negative
-2.
2 over negative 1/4. Do you agree with that? This would be my, if I did that correctly. Let's see, did I do that correctly? Over.
No, you dropped the 2a
Thank you.
or the 2.
There we go. Well, I can cancel all over the place. So what would that be?
4. Negative 4.
Negative 4. So well, check this out. I'm going to go way out on a limb here. X minus negative 4 is x plus 4. Now all I got to do is figure out what goes here. How do I figure out what goes there? Take the negative 4, put it in there, and whatever you get, that's going to be what goes here. Right? That's your other thing. All right, so let's figure that out, whether with a calculator or by hand. So I have negative a fourth times the square of negative 4 minus 2 times negative 4 minus 2. That's negative a fourth times 16 plus 8 minus 2. So negative 4 plus 6. That's, after all is said and done, that's just 2. Okay, plus 2. Now, how do I know that's going to be true? I'm pretty sure this is the right equation. Okay, you guys okay with pretty sure this is the right equation?
Wait, well, what's the 2 again, please? I missed that.
That's the K.
And how do you figure it out?
I just took the negative 4 and evaluated.
Oh, okay.
Now, I'm saying this is equal to this, and I'm pretty sure I did it right. Okay, the fate of the universe rests on us getting this equation right so we can send the rockets in the right direction to blow up the meteors and all that kind of stuff. Can you be absolutely sure you did it right? How can I be absolutely sure this is correct?
You can
Multiply it out.
Multiply it out. It would be really silly to say I'm pretty sure I'm okay. How about that'd be negative a fourth x squared.
Negative 2x.
2x minus 4 plus 2 is negative a fourth x squared minus 2x minus 2. Okay, yeah, I did do it right. I don't ever need to see this. It's just sort of assumed that you would check it because the check is really easy. But if I make an error, then all of my conclusions will be about a different problem in a sense. Now, can you tell me what the vertex is? I'll just call it big V. Remember, the form is x minus h quantity squared plus k.
-4, 2.
-4, comma 2. And by the way, the vertex is the most important piece of the puzzle. And if I do it right, I can always read the vertex right from my equation. Now we need to figure out the p. We need to figure out the focal length. Okay. Now, you never have to do this, but it's always a really good idea to do this. -4, comma 2 is here, and you said it opened downwards.
Is it -2?
Do you agree that it's going to look something like this? Something like this. So is the focus above the parabola or below the parabola?
Depends on how
Below.
how the parabola
Below.
opens.
This parabola looks like this. So focus is on this side, which means the directrix is on that side. Why? Because if the directrix was on this side, it'd intersect the parabola. Oh, so tell me about my value of P. It's going to be
Negative.
negative because I have
Or
to
at
do
least
the
less
other-
than 2.
And how do I know it's going to be negative? All right, there. Now, what does 1/4P equal?
Professor, quick question just about the remark you just said. Could we just say it's just less than 2? We don't know if it's negative because it could be at 1, if like depending on how the parabola.
Oh, I'm not talking about the coordinates of we're talking about the focal length. We're just trying to find P. P isn't a
Oh,
coordinate.
okay.
P is a distance. Think of P as what am I going to add? You're right.
Right.
It's going to we're mixing.
I understand what you're talking about now. Yeah.
The y coordinate of my focus is smaller than 2. You're absolutely correct. Whether it's positive or negative, I don't know, but I do know the value of P is going to be negative because it's going to send me in this direction.
Yeah.
Now, might it be here? Sure. Might it be here? Sure. I just know it's on this side. That's the important thing. What does 1/4P equal?
-1/4.
-1/4. It's that simple. Because we showed this is 1/4P. Well, based on this, what's P?
-1.
-1. Aha. So can you now tell me the rest of the puzzle? Absolutely. What's your focus?
-4, comma 1.
1, because I added that to the y coordinate, and we just agreed the focus should be on that side. What is the directrix? I went
Y
1 in this
equals
direction. Now I need
3.
to go 1 in the other direction. So it's the line y equals 3. That's it. We're done. There is absolutely nothing else we could say about this parabola. We have this equation. We rewrote it, and often this is referred to as vertex form. You know, when you have the equation of a line in algebra, you often like to write it in slope-intercept form, because in slope-intercept form, you can read the y-intercept, you know what the slope is, and therefore you know a lot more about the line. Slope-intercept form is not required. It's just by far the most useful form. This is correct. This is the most useful form because I can read the vertex. I can read the direction. I can figure out the P. That's why you always want your parabola in this form, because then the rest of this becomes really, really simple. So we just took this equation and told everything that's conceivably possible to tell. And there's nothing else I could possibly tell. So that's starting with the equation, deriving information. Now let's do the flip side. Let's do one where we have some information and we're going to figure out the equation. Because it's really the only other thing we can do with a parabola. Okay, let's suppose the instruction will be find the equation, or technically it's find an equation, but the form, we all want the same form, of the parabola with focus 6, let's say 6,3, and directrix. How about the line y equals, let's say y equals 2. So if I was to draw this thing, okay, is this going to open up or down?
Up.
Up because the focus is above the directrix, and it's going to probably be ish. You never have to do what I just did, which is why you probably always should do what I just did, so that when you get your answer, you go, okay, good. It agrees with what I said it should be. In other words, I have an upwards opening parabola that sits in between there. I got to get that right. Now, I didn't tell you the axis of symmetry. I didn't tell you the vertex. I didn't tell you everything. What's the very first thing I can figure out based on this information here?
We can figure out the axis of symmetry.
And at the same time,
The
the vertex.
So the vertex is just the in between the focus and the directrix, right?
Yep. So what would my vertex be? Right here.
2.5.
It's an ordered
Six.
pair.
6,
6 comma.
2.5.
So therefore 6 comma. There's no place that I can think of in the history of mathematics. There's no place where you can actually insert a mixed number into an equation and actually be successful. No, improper fraction. There is no scenario that exists where if you put a mixed number, you'll actually get the answer, because the algebra of mixed numbers does not exist, because a mixed number is a sum. So when you raise it to power and take roots and do things, people forget it's a sum. So
5
all
over
the rules
2.
fail. Yeah, I'll always do this, because the rest of it, can you now tell me at least a lot of the equation? I'm gonna put blank x
minus 6.
plus
K, which is 5
3
halves.
halves.
how about
5 halves.
5 halves? I'm leaving a blank here. What goes here?
1 over 4p.
1 over 4p. Oh, we don't know what that is yet. Do we have enough information to figure that out? You said that point right there was 6 comma 5 halves. So to go from 5 halves to 3, how big is p?
1/2.
In fact, I'm going to write it. P is 3 minus 5 halves. Do you agree? That's what P is. And I went the other way. Oh, okay. So what's going to go here? What's 1 over 4P? That'd be 1 over 4 times a half. And that is
1/8.
1
No,
half.
no, 1/2.
it is 1/2, isn't it? Okay, now what? We're done. There's nothing else to say. I gave you the focus and directrix. We figured out the vertex, and now we have an equation. That wasn't bad at all, was it? And by the way, it doesn't matter if the numbers themselves are, just horrific and fractions all over the place. The process is always going to be exactly the same, because our goal is something of the form x minus h quantity squared plus k, knowing that the 1 over 4p is in front. So either I'm given p or I have to figure out p. But without the value of p, you can't finish the problem. So there's always going to be enough information for you to find p. Now, why do we study parabolas? Because I said in the business model that we talked about, the downwards opening parabola, figuring out equilibrium, all of that stuff is really, really valid if you're in a business class. You're not in a business class. And parabolas are a geometric shape. There's no geometry in that example. In fact, there's no 3 dimensions in that example. So what makes a parabola interesting? A parabola is very interesting in how it relates to things like sound waves. And I'm going to give you some really simple explanations of how a parabola works, because the whole thing about, the distance here. So I'm going to give you an example that I love to share with people. Hold on. I gotta have a better eraser than that one. Oh, good. That eraser was starting to die on me. Okay. Now, if you've ever done any form of billiards, you would understand some of what I'm going to talk about. Now, I may be the world's worst pool player because I cannot see the white ball and the ball on the other side and see them both at the same time. I'm terrible, but some of you are probably really good. I wouldn't mess with you, right? So you have a typical billiards table, and you've got the ball. Let's say it's here, and then your white ball maybe it's here, and you want to do things like maybe hit it at exactly the right angle to knock it in, or maybe you want to bank it. You want to knock it into a pocket, and of course, if you're a real pool player, you would call your shot, right? Otherwise you don't get it. So it's all about geometry. Now, here's why I'm going to take this out of the equation. No backspin, fancy moves, jumping over. No, I mean, you're just hitting the ball straight. It's hitting the other ball. So when I play pool, I use a lot of geometry. See, this shot for me is trivial. Put that guy right here, and I'm probably going to miss it. It's too far away. But I am really good when it comes to the geometry and trigonometry of pool. I say, how is that possible? For example, when I'm looking at this, I'm going, okay, I walk over and I look exactly, I need to hit it. Okay, I need to hit it right there in order to knock it in. Okay, some of you know that. But what if I want to knock it in here? That's more interesting to me. So there's simple geometry that takes place. Wherever this hits here, it must bounce off at exactly the same angle. That's geometry. Whatever angle it makes, it has to hit. So when I'm doing this, I'm figuring out what angle it needs to hit at in order to go in. So I'm going to hit it in such a place that it hits exactly the side. I actually will sit there and do this to the annoyance of my wife, who's probably the only person I played pool with in the last 30 years. But I'll do this and I'll make the shot. Of course, I can't hit the easy ones, but it's all about angles and when it bounces, and that's the key. This is where parabolas come in. The angle that it bounces off when it hits something. So just in general, if I just say, here's a line, and you're going to throw a rock or you hit a ball, and you're going to hit it right here. Do you know you can figure out exactly how it's going to bounce off? Because if I take the perpendicular to this, then whatever that angle is right there, oops, everybody understands what I'm getting at? It has to bounce off at exactly the same angle. That's just simple physics. You with me so far? So you said, how does that help me with a parabola? Well, this is why parabolas even exist. We're going to consider a really simple situation here. I've got a parabola, and it doesn't have to be infinite. And I've got, let's just say hypothetically, there's the focus right there. Now, I can prove this to you on another day separately because this takes a really long time, but it's all algebra and geometry, the proof. If I said, let's do a line segment through there. Turns out it's going to bounce this way. If I want to go, or maybe I'll just go like that. Boom, it's going to bounce this way. Well, if I hit it over here, it's going to bounce this way. What if I hit it over here? It's going to bounce this way. And we talked about that just a moment ago. If I said, consider the perpendiculars going through here, that's the angles that are made. That it's the tangent line here, the angle here, angle here. But if I'm coming from the focus, no other point, only the focus. If I'm coming from the focus, every time they bounce, all of the directions are parallel. That's an absolute. And I can prove that to you using nothing more than geometry and tangent lines, little calculus, of course. Well, why would that be interesting? All right. Let's make this three-dimensional. Now it's called a circular paraboloid. This is the shape we study more than anything else in Calc 3. Oh, better yet, I still have a focus here. Now it's in 3D. But now I can go forward, backward, in every direction. Let's put a light source. A light bulb.
I was going to say, it looks like a headlight.
Let's put a light source there. Then I can actually generate a narrow beam of light. Now, if I had a torch in my hand, right, it just glows spherically and dissipates really, really quickly. But if I put something around it, maybe to channel it, I might be able to create a beam. Now, here's the idea. We might be able to make some money on this, folks. What if I took one of these and made it small and I could put it in my hand? I could go outside at night, maybe. Or like I said, I could put it on the front of my car and I could drive at night, or better yet, we could point it up to the sky and call Batman when we need to. Or has somebody already beat us to it? Have you ever taken apart? I think I have one here. Hold on a second. I used to have one here. Did my? Oh, it's gone. Oh no, it's not. It's right here. No, this is a lousy one. Okay. You ever take apart one of these and actually look? No, this one doesn't come apart. Take apart your flashlight and look at that part. It's going to be a parabola. If you've ever replaced the headlights on your car, you already know this. Perfect parabolas. And by the way, if it were any other shape, it wouldn't work. And if the light source was anywhere other than the focus, you don't get a narrow beam. You know, the last one is that searchlights. Now, these are parabolic in nature. They're perfect parabolas. They cannot be a flaw or you won't get the narrow beam of light. So in terms of light sources, it's unbelievable. It's so cool, but it's way cooler with sound waves. Now, football season rolls around and some of you guys will watch football and there's always that person standing on the sidelines and they'll have the big, I don't know, conish looking thing and they'll be pointing it at athletes and they, to hear the conversations. It's not hooked up to anything. And usually it's whatever athlete they point at always seems to swear right at that moment. But you guys have seen that when they're pointing and they can hear. It's like, how are they doing this? Police in certain areas will drive by with these really heavily armored cars and they'll point things at people's houses and they can hear every word spoken. This is a thing. It's not a thing.
Wait, they do that?
Say again?
They do that?
In big cities, yeah, they do that a lot, especially in areas where they're thinking there might be some, bad people hanging out.
Professor,
Investigate.
I don't want to stray off the conversation, but it's this specific technology you're talking about. They're also doing it. I watched a TED talk about it, that it's speakers that are directional, and literally unless you point the actual speaker at you, you cannot hear from that speaker.
But my point is the speaker's parabolic. Okay.
Mhm.
So these now Reuben H. Fleet Space Center in Balboa Park. I was parent helper many times over the years when my kids were going through school, and that was always the second grade field trip. They'd go to Reuben H. Fleet. Has anyone, just say out loud, has anyone here ever been to Reuben H. Fleet Space Center? It's cool. You know, you have all those things, places where things are floating up in the air and all sorts of really weird science stuff. That's not it. There's a place that if you stand, now when I've been there, you have to understand there's hundreds of second graders running around screaming, causing mayhem, and it's just the way it is. I actually met Junior Seau there once. He was doing the exact same thing I was, and I was pretending not to know who he was. He was still playing. 6'5", 250. He was wearing a shirt about 20 sizes too small as his arms were bursting out, but he was there with his son. So we were having fun. We were just talking about how goofy it was. But there's a place if you stand there. So Yaman's on the other side of the room, and I'm like, Yaman, afterwards, let's take off and get some wings. And he's like, I can't hear you. Oh, move over a couple of feet. No, okay, Yaman, let's sneak out here and go grab some wings. And then I move over here. You can't hear me if I yell. I move over here. I can whisper across the room. How many know what I'm talking about? It's the most crazy science you can imagine. There's no microphones. There's a spot that if I stand in the right spot.
Oh, they do that. They do that with stages. It's like the acoustic something.
It's parabolic, and if you stand right at the right spot, you're standing at one focus. The other person's maybe 100 feet away, standing at the other focus, and I can whisper with all the screaming going on, and you can hear me as if there's no one else in the room. It is so unbelievably cool. You move a foot in either direction, no, it doesn't work, because it's based on standing at the focus of a parabola that's pointed at the other. Two parabolas pointed at each other, quite literally. But you don't realize that when you're standing there. It is so unbelievably cool. And this is parabolic. Parabolas can channel sound waves. That's still not even close to the coolest thing that I've ever seen. Now, unfortunately, as the years have gone on, I can only tell you about this story. You won't experience it. Over the years, I've had many students who've experienced the thing that I'm talking about, but now I don't think you can anymore. I got married. Next month, it'll be 30 years, actually. And we did our honeymoon in Cancun. And not that far on a rickety old bus ride, there's ancient Mayan ruins that had only recently been uncovered in a place called Chichen Itza. It's one of the most important, historical findings, but they hadn't been that long when they found this. And we took a bus ride and spent a day there. They had a pyramid that is so ridiculously steep that when you climb the pyramid, I'm not joking, you climb it like this. You put your hand in front of you on the steps because it's so steep. And if you slip, that's bad. Nowadays, they don't let anybody on the pyramid. They haven't for many, many years. That was a bad idea then because of the erosion and things. They were unearthing gigantic structures at the time I was there. They were still digging and excavating, but they had unearthed a stadium, an entire stadium. I mean, quite literally like a football stadium. The walls went straight up, I want to say 30 or 40 feet. And the engineering, now you have to understand, this was 3,000 years old. Just the technology to make things geometrically as perfect as they did was pretty amazing. But this was 3,000 years old. They'd been buried under dirt for centuries. But as you walked across, they had like hoops way up high. And we were asking questions, and the guy said, well, they played a form of soccer in the stadium, and the stands were filled with thousands and thousands of people. They played a version of soccer. Oh, hang on one second. I'll turn that off. Now, I always have fun with this because you have to understand a soccer ball, any type of basketball, those were still a few thousand years away from being invented. So the quote unquote soccer ball, does anybody know what they played with? This is traditional historical all over the world.
Just a solid rubber ball.
Well, that rubber was still a couple thousand years away from existing. No, pretty much this is true in old.
Bag of sand.
Oh, human head.
The head of the deposed clan leader that they had recently defeated.
Nice.
You put it in a bag and you kicked it around.
Solid.
If you've ever watched movies, yeah, it's kind of, that part's kind of creepy, but that's traditional. That's, by the way, I don't know. Hopefully that's not still going on. Hopefully they use soccer balls now. But he said there was a person that they would address the crowd, kind of like in the Roman Colosseum before the gladiator match. You'd have the one person in the middle. He's addressing the crowd. But now understand, there's thousands of people. This is a stadium. It's a rectangular stadium, not as big as a football stadium, but maybe, much bigger than a basketball arena. And the guy said, okay, he said, here's what I want you to do. We're on the floor of the stadium. He says, I want you to clap and just walk really slow. So you clap, and then you got to a point and the sound vibrations almost hurt your ears. It was like, whoa, that was weird. Nothing. I moved to a spot. The sound vibrations almost hurt your ears from your own clapping. They had created a situation where if you stood in one spot in the stadium, like the Reuben H. Fleet Space Center, a person could stand there and talk at a normal tone with 30,000 screaming people in the stands, and every single person could hear him clearly. And it was because you could see the parabolic backgrounds of where they created the situation. Now, understand that the geometry we're talking about, most of this was developed by the ancient Greeks in the 4th century BC. What I'm talking about preceded that by like 1,000 years. And they were able to figure out a place where, better than a microphone, a person could stand and be heard because of the parabolic nature of the sine waves. To me, that's still maybe the coolest thing I've ever seen from an architectural scientific thing. And I wouldn't have believed it if you told me. I was actually there experiencing it. What I've heard though recently over the last few years is I've had students tell me that they've been there and there were certain things they were allowed to do, but nowadays they won't let you into any of these things because, again, with tourists on a daily basis going through these things, destruction is inevitable. Not because people are being careless, just the sheer number of bodies passing through and walking on and stuff. So I don't know that anybody's ever going to get to do this again, but it's unbelievable. But parabolas we study because of not just their geometric purposes, but they're actually used in engineering to do things. Sound waves, light beams, things like that. So the stuff that we did in algebra where we drew that graph and we found the intersections of the x-axis, that's all well and good. That's algebra, but you could do that with any shape. So parabolas have their own like little special place in our hearts right now, okay? Now, tomorrow we're going to look at ellipses and hyperbolas and look at some of their geometric characteristics, and also where the heck are they used in real life? You see, if we just studied parabolas and I didn't tell you all this stuff, you'd say, why do we study parabolas? Why is it even important that we study parabolas? Yet, the further you go on, it's one of the most studied shapes that we have for good reason, because again, their uses. So let's stop there. Oh, started to freeze on me there.